Okay, so now that we have the basics of what Biot-Savart actually tells us, let's go ahead and do some example calculations with that. I'm going to do two. I'm going to do the finite segment of current that's straight. That's going to be a little bit challenging, and then I'm going to do the circular current. And if this is seems like strange deja vu, because we did basically these same things in the electrical picture before. We did a finite rod, and then we did a ring before, so now these are just the magnetic versions. So we're going to do these. Those are going to live on the equation sheet, and so if you see these again in the future, then you can of course just use them, but pay attention to the techniques being used, because if you need to synthesize these on your own, then you can find those magnetic fields as well. So first of all, let's go ahead and start. Here I have a finite segment of wire. It's going to have a current I running through it. It's going to be of total length D. And I'm going to ask, what is the magnetic field up here? So I'm above the end, and I'll call my distance above the end R perpendicular. And let's take a look at how to do this. Let me remind you what the Biot-Savart Law is. I'll just copy it over here. And let's get started. So first of all, this proceeds very similarly to what we did back in the electrical world. We're going to pick some arbitrary little chunk of this. That's my point current, so to speak. And that's what I'm going to integrate up from. So I'll call this my little dl. And remember, it has a direction that points along with the current. And again, how you want to do this, you just want to kind of pick as arbitrary of a dl as possible. That way you're not committing to saying something that isn't true for all of the different parts of it. So if I just pick the one at the very end here, and then of course then I'm committing myself to a special case. And then you're going to integrate over dl, which is where the current lives, over dl, which is where the current actually is. So in my case, I guess I'll go ahead and put some axes here. I'll call this the x-axis, and I'll call this the y-axis. And so my integration here, my dl, is going to be a integration over just x. And you can probably already see that since the current actually lives here only, my integration bounds over dx are going to be from x is minus d to x equals 0. So it starts from here, goes to here. You have to integrate in the same direction as the current is actually going. So now you may wonder, why did I set my axes so that I have to start at minus d and go to 0? It makes it a little bit easier choice than some others. And then you're going to kind of set this up, and you're going to go through a similar process, and when you integrate this, you're going to decide which terms are constant and can pulled out of the integral and which aren't. But I'm getting a little ahead of myself here. Remember that I have this unit vector r hat. That's going to point from my point current to where I'm interested in finding the field, right here. And then this is the angle. And that angle does need to be considered, because the sign of that angle is going to determine whether the contribution made by one of these point currents is larger or smaller. So, so that is going to play a role here. And of course, the reason I use r perpendicular here is because the r in this equation is the distance from the point current to the point in question. So that I'm reserving for r. Whereas r perpendicular, which is just your distance above the end, I'll call that with a different variable just not to get them confused. So now I'm going to go ahead and just start looking at, oh, and I guess before I do anything else, I should, of course, I'll put my thumb along with the current. The magnetic field everywhere above goes out, everywhere below goes in. So at this point in my question, the magnetic field definitely points out of the page. So I've already gotten that taken care of. I just need this integration to provide me the amount, the equation. So let's go ahead and get started. Let's take a look at, in this equation, what's constant and what's not constant. This is a big thing when you're setting up these integrations. So which of these variables is the same for every one of these little segments, dLs, and which one isn't? Well, first of all, of course, I'll get you started. Mu naught and 4 pi, those are constants. Those can always be pulled out. The current is also a constant. Every single one of these segments has the same current, of course, because this is just the same wire that the current is going down. But things that are not constant are the theta and the r. So you can see that depending on where you are along this, these little segments are gonna have different distances. So this distance changes. So the r from each one is going to be different, and this angle is going to change as well. So those are all different. And so I'm going to have to reconcile these somehow to my integration variable, which is going to be x. So let me take care of that in just a second. But for now, let me go ahead and pull out all my constants. And then over here, dl is now going to be just dx. And then sine of theta and r squared, I'm going to have to leave those in there because those are going to be changing. And of course, I'm integrating here to get b. Okay, so first of all, let's go ahead and try to figure out how we can put these in terms of x, right? If this is going to be integration over x from minus d to 0, then I have to have theta and r play nice. So this right triangle right here, this is the x coordinate. So you can, let me redraw it over here. We have this nice right triangle, r perpendicular, r, x, and theta. And hopefully you can see from there, well, r, of course, this is just square root of x squared plus r perpendicular squared. So now I've got that in terms of x, and r perpendicular, of course, that's a constant. So it doesn't matter which of these segments I'm talking about here. If I were to sketch this, their x values are different, but they all have the same, basically, y value to get up there to the point in question. So that's there. And then as far as theta goes, well, I have sine of theta here. So looking at this, sine of theta, which is really all I need, sine of theta is opposite over adjacent, or putting in like so. And so you can see now I've got sine of theta in terms of r perpendicular, which is a constant, and x. So now I've got everybody on the same nice playing field. I go ahead and put all this back in. Mu naught I 4 pi, and then this is integral of dx, and I'll put in my sine of theta, r perpendicular over this stuff. From there, I'll put in my r squared itself, so that'll be in the denominator. I'll square that. And this thing right here, this of course is an additional constant that I can pull out. And so let me write it over here. Mu naught I r perpendicular 4 pi integration, and then I'll combine these, square root of blah times blah. That's blah to the 3/2. And dx. And I'm going to integrate from minus d to 0. So now I've got something that looks like, it's from math class. I'm clearly going to integrate over x. I've got this constant that's stuck in there. Oops, I forgot there's a square in there still before I raise it to the 3/2 power. And if you want to impress your calc teacher by remembering this is a trig sub, or this isn't math class, so we're just going to go ahead and grab the result from the third page of the equation sheet, which has a little mini integration table. So let me go ahead and copy it here. We have mu naught I r perpendicular over 4 pi, and then this result comes out to be, let me just copy it from the integration table, x over r perpendicular squared, square root of x squared plus r perpendicular squared, and of course I still have to evaluate it from minus d to 0. And before I even do that, let me let these two cancel a little bit. So I'll pull that out here, the r perpendicular that remains, and then I'll evaluate. So that sort of got pulled out there, and let me evaluate this. So if I plug in x equals 0, I do actually get 0 here, and then minus, and then I'll put in the other limit, minus d over d squared plus r perpendicular squared. These two wipe each other out, and I have my final answer, mu naught I over 4 pi r perpendicular times d over square root of d squared plus r perpendicular squared. So, if you look at this, it's not terribly impressive. It is the final answer for the strength of the magnetic field. I want to show you an alternative expression for this that is incredibly much more handy. And in order to do that, I want to go back and redraw this. Here is the whole thing, the whole current segment. It's of length d, and I am a distance r perpendicular above the end. And what I want to look at, there's a right triangle that can be formed with just looking at lines that you take from the point in question, and you connect. You basically say, how far am I away from this end and how far am I away from this end? And if you look here, if I call this angle, I don't know, I'll call this angle theta from the end. This is not just any arbitrary angle, but this is the angle from the other end, theta sub e, I guess I'll call it. If you look, then the cosine of that angle is d over this length, which is of course by Pythagorean theorem like this. And hey, look at that. That is exactly the expression I have right here. So I could express this whole formula as this. I'll give you yet a better option. Let me call this complementary angle inside this right triangle, I'll call that phi. Okay? So that, of course, phi and theta add up to 90, and you may remember this, hopefully remember this property from trig, that the cosine of an angle is equal to the sine of its complementary angle. And so I could also replace this by sine of phi. And that is going to be my final expression that I'm going to use. So it took us a while to get there, but this is definitely what I think is the most useful way to express this. And it is also going to allow us a number of different extensions to this equation. Now you might say, why is phi better than theta? Let me show you why. So let's say you have this current segment, and it's a distance d, okay? And you're over here. I'm going to draw a little cartoon person. And what I'm going to ask you to do is imagine that this cartoon person is essentially going to just point one hand toward the near end and one hand toward the far end of this segment, like this. So So you can just kind of imagine that they're kind of pointing one hand toward each end, and look at what angle their arms make to each other. That's phi. So all you need to do is know, okay, how far are you away from this current segment at your nearest, which is our perpendicular, and what angle do you need to make with your hands to span the two ends, so the near end and the far end. And if you look, that angle, that distance, and the current will tell you the magnetic field that you're experiencing from that current segment right now. So what is the magnetic field strength where you are? So I think that's makes phi a much more intuitive angle than theta, because theta is over here. But if you're actually standing at the point where you want to know the magnetic field, and you're sitting there saying, how far am I away from this thing at the closest, and how much of an angle do my two hands make when I'm spanning the near and the far end, and that's all the information you need to get the magnetic field that you're experiencing. So let's just go ahead and extend this. There's a lot of different applications we can make to this. Let's just take this and run with it. First of all, let's talk about what I call a semi-infinite wire. So a semi-infinite wire would be one that basically ends right where you are. Okay, so here's your R perpendicular. But it came in from forever. So if you look at that, if you span the angle that this thing makes, well, if this thing goes on to forever and ever, okay, then this angle gets larger and larger, and in fact it approaches 90. And so in this case, the angle phi would approach 90, and let's see what would happen to the formula. Well, B mu naught I over 4 pi r perpendicular sine of 90, well, sine of 90 is 1. And so if you were here, you would experience a magnetic field of this. So if you're standing right above the end of a semi-infinite wire, then where the current comes in from very, very far away and stops right next to you, then that's the formula to use. So that's one example where we can apply this, kind of extend this formula. This formula we can extend it in a number of useful ways. What about if you were not above the end, right? So that's obviously a very important case. We're not always just going to stand next to the end of wires. So what if we're not at next to the end of a finite wire? So something like this maybe. And let's say we're not even at the perpendicular bisector. Let's just say we're at some random location. So our perpendicular, and we want to know what the magnetic field is right there. So I guess I'll draw that person again. Maybe I'll just draw their arms. Here's a way to think of it. Split this current segment into two, the part that is on one side of you and the part that's on the other. And I should draw the current here. The current goes like this and the current goes like this. So split it into two parts. So you're above the end of this part and you're above the end of this part. So we can essentially use this formula twice. So remember this trick where you basically just have to span your hands, and your hands, one goes to the near side and one goes to the far side. And so over here on this left segment, this would be the angle that it spans. I'll call that phi 1. So the magnetic field that you'd experience here would be mu naught I over 4 pi r perpendicular times sine of phi 1. Okay, so that would be from that one. That's just a repeat of what we did over here. However, I should point out that if you do the right-hand rule on either of these currents, you point your thumb along the current, the magnetic field comes out. So it comes out from this segment, out from this segment. So the magnetic field here is going to be definitely out of the page. It's just additive. Okay, so both of these segments will contribute the same way. And if you look here, well, of course, you're above the end of this one, and the angle spanned by this one will be this angle, phi 2. So mu naught I over 4 pi r perpendicular sine of phi 2. So, of course, all this stuff is shared, same current, and your same distance above the end of both of them. So you just factor that out, and presto, you can now figure out what magnetic field you're experiencing if you are at any point, not even on the bisector, but at any distance along a finite segment. Okay, all you need to do is be able to measure the angles of the basically to one end and to the other end off of the perpendicular distance. So this you can use a bunch. There's a homework question where you use this quite a bit as well. And of course, what this allows us to do is go to the truly infinitely length wire. If both of these, this comes from forever and goes to forever, then both of these angles will go to 90. Phi 1 and phi 2 both go to 90 degrees. And what that will cause, and I guess I should draw a picture of this. So this will look like this. This goes on like this. This goes on like this. And you're interested in the magnetic field right there. It's going to point out of the page. And this is our perpendicular. So if both of these go to 90, then over here, just using this same equation, this becomes 1, this becomes 1, just like it did up here. That becomes a 2 overall, and that 2 cancels with this over here, and we get the magnetic field is mu naught I over 2 pi r perpendicular, which that's, of course, one of the workhorse formulas that's used over and over again in the previous lecture videos, because when you have an infinite wire, you can basically easily say what the magnetic field is everywhere. At this point, usually, the integration is long forgotten, and so the distinction between r, which is used in the integration, and r perpendicular is kind of washed out. So just to avoid having to write the perpendicular thing all the time, you just use mu naught I over 2 pi r, where r is just your closest distance away from this wire. So now, of course, you've seen this before. We've sort of showed where it comes from, but you also have a lot more options on finding the magnetic field near things. Are you above a semi-infinite wire? Are you not at the end of a finite wire? Are you above the end of a finite wire? So these are all things that you now can find should you need to do so. This does live on the equation sheet, so you don't need to rederive it by any means. But hopefully, in showing you where it comes from, it gives you some new techniques to put into your bag, and you understand how to apply these a little bit more carefully in the process. Now, there's one more thing that I said I would do for you. That would be the circular current loop. And if you're thinking that was really difficult, what we just did, then you'll be glad to know that this is extremely easy in comparison. It's not too dissimilar to when we were doing electric fields. That finite line charge took us a while, but then the ring was pretty easy. So this is kind of the same thing. So I'll go over here. I'll draw myself a nice circular current loop. I'm going to call the radius of it r. And I am going to find the magnetic field right in the middle. So looking right here. I'm not going to do it. This is not valid anywhere on the central axis. It's just in the exact center. So center only. So unlike that ring thing we did earlier in the semester, this is only good exactly in the middle. It's not that we couldn't do the other one, but let's just try to maintain some limits here in terms of what we look at, not keep this lecture from getting too long. So let's go ahead and do this. I'm going to pick some arbitrary DL. Really any point will do. Let's look right here. This is my DL. It's a little segment of length that points with the current. R hat, that is the little unit vector that points to where I want to know the field, so right there in the middle of the circle. And let's take stock, what's constant and what's not. So mu naught and 4 pi, of course, are always constants. The current is a constant. And now, theta is constant. In fact, the angle between DL and R hat is always 90 degrees, so theta is a constant. In fact, sine of theta is going to be 1, because that's always 90 degrees for every single point along here. And also, the distance from each of these segments to the middle is, of course, all the same. Every single little segment on this thing is a distance, big R, from the middle. And so there's nothing that's not constant. This is going to be super easy. When I integrate, I put mu naught over 4 pi I. Sine of theta is always 1, so, and then this is always a big R. And then all I get is integral of dl. So, integral of dl is easy. That's just L. That works whether you have a subset of a circle or not. So just as a homework hint, there is a problem where you have a partial arc length, you don't have a full circle. It's still all valid. But of course, in my case, I do have a full circle, so the length of a circle, or also known as the circumference, is just 2 pi r. So, putting it over here, get a lot of cancellation. Pi's cancel, r's partially cancel, these partially cancel, and what I'm left with is mu naught I over 2r, which again was kind of just thrown out there as a given formula earlier. Now we actually understand where it comes from, and if I were to go and ask you what would it be for just a partial circle or partial arc length, you hopefully have now an idea of doing that. And of course, the other thing I should mention is if you happen to have just a few of these, so that they're all basically wrapped in the same place, then you can multiply by the number you have. So that's the way the formula was presented as well earlier. So that'll do it for the Biot-Savart law. Hopefully you understood those examples enough so that if I do, or I should say when I do ask you on the homework to do these integrations yourself, that you're able to do that.